What if the quietest parts of the universe hide the most unsettling truths? Out there are stars that can erase themselves in a blink, and regions of space where even light cannot find its way home. Tonight, on Sleepy Traveler, we will drift gently through these shadowed wonders. There is no rush. Nothing will reach for us here. We are only listeners, floating safely while the universe shows its darker shapes from a distance. If these calm midnight journeys feel right to you, a soft like and subscribe can help other wanderers find their way here too. For now, settle in and let the night open as we begin our quiet descent into the deep. Far away from the comfort of our night skies, the universe can be a harsh and restless place. Out there, worlds are torn apart, stars grow hungry, and invisible storms sweep through space with a kind of quiet cruelty. Planets can be stripped to their cores, whole systems can be rearranged, and delicate atmospheres can be erased in moments. From the softness of our own blue world, it is strange to imagine places where the rain could be molten metal, or where a star might suddenly blaze brighter and scorch everything that circles it. Yet somehow, knowing these things exist can make our own fragile safety feel even more precious, like a small candle glowing in a vast, dark hall. Among the most unsettling things to picture are worlds that do not belong anywhere. Rogue planets. Imagine a planet with no sunrise, no warm star rising over its horizon, no seasons to measure the passing of time. Just a lonely sphere drifting through darkness, lit only by distant stars that never grow large enough to cast shadows on its surface. These wandering worlds do not orbit a sun. They are not anchored. They drift freely through interstellar space, silent and almost invisible, like ghosts moving between the constellations. Many of these planets may have started life in an ordinary way, circling a young star in a crowded newborn system. In such places, gravity is a restless sculptor. Giant planets can shift their orbits, sweeping through the disk of gas and dust. Smaller worlds can be nudged and jostled, their paths twisted into loops that grow more and more unstable. Every so often, the pushes and pulls line up just wrong, and a planet is flung outward beyond the region where its star can hold it. Once it crosses that distant boundary, there is no gentle path back. It slips free and keeps going, leaving its home star behind, like a lantern fading in the rear view of a long, dark road. Some planets may never have had a home star at all. In certain quiet pockets of space, clouds of gas and dust can collapse just enough to form planet-like bodies, but not enough to ignite a star at their center. These worlds are born in darkness, never feeling the close warmth of a sun, only the faint inner glow of their own leftover heat slowly fading over ages. If planets can form in both ways, thrown out of systems and born entirely alone, then the number of these drifters might be enormous, far greater than our early guesses. Because rogue planets give off so little light, finding them is like trying to notice a ship on a moonless ocean with no lanterns lit. Astronomers have learned to look for their presence in indirect ways. One of the most delicate methods is called gravitational microlensing. When a massive, unseen object passes in front of a distant star, its gravity bends the star's light ever so slightly, making the star appear to brighten for a short time. By patiently watching for these brief, subtle flickers and measuring how they change, scientists can infer that some hidden world has crossed the line of sight. From these ghostly hints, they have concluded that there may be as as many wandering planets as there are stars, perhaps more. Most of those worlds will never come anywhere near us. They will drift through the galaxy, untouched and unknown, their stories forever silent. But if a large rogue planet wandered close to our solar system, its gravity could quietly rearrange things. Far beyond Neptune, in the icy outskirts, countless frozen bodies circle the sun along slow, distant paths. A passing giant could disturb those orbits, nudging some of that icy population inward, turning a few of them into long-period comets on new, dangerous trajectories. In a more extreme case, a rogue world could plunge through the outer system itself, twisting paths and pulling at planets until familiar orbits became unpredictable. Some astronomers have even wondered whether an unseen giant might already exist on the fringes, a hidden member of our own family that has yet to be clearly found. The orbits of certain distant icy objects seem to be tugged in similar ways, as if something heavy were shepherding them from afar. This hypothetical world is sometimes referred to as Planet 9, a distant, cold giant lurking beyond Neptune. If we struggle to detect even a possible companion in our own backyard, it is a quiet reminder of how many truly rogue planets might be gliding through the greater dark, completely unnoticed. Not all doomed worlds are flung outward into isolation. Some are bound to their stars so tightly that their fate is to fall inward instead. These planets circle so close to their suns that their orbits slowly decay, tightening like a spiral drawn on invisible paper. They live in a kind of slow, inevitable collapse, each trip around their star bringing them a little closer to a fiery end. Astronomers have discovered several exoplanets that seem to be trapped in this kind of death spiral. One of them is called Kepler 1658b, a gas giant similar in size to Jupiter, orbiting a distant star thousands of light years away. Careful observations suggest that its orbit is shrinking bit by bit. The reason lies in the tidal pull between planet and star. Just as our moon raises tides in Earth's oceans, a star raises tides in a nearby planet, not just in its atmosphere or seas, but in its entire structure. This stretching and squeezing turns orbital energy into heat inside the planet, causing the orbit to slowly lose energy and contract. In our own system, the effect works the other way around. Tidal interactions cause our moon to drift slowly away from Earth. But in systems like that of Kepler 1658b, the planet is the one moving inward, step by small step, unable to escape the star's grip. Another doomed world, known as WASP-12b, circles its star so closely that it is being pulled out of shape. Instead of a neat, round globe, it is stretched into something more like an egg, forever being tugged by the star's gravity. Its atmosphere is being peeled away, gas streaming off into space like a glowing veil. Over time, the star will feed on its own planet, stripping it down until little remains but perhaps a bare, scorched core or a whisper of dust. For gas giants like these, the journey inward is both violent and slow. As they draw closer, their atmospheres heat up dramatically. Winds roar, storms swell, and the upper layers puff outward, making the planet larger and more vulnerable to the star's pull. Some of that hot gas escapes entirely, forming tails that trail behind like those of comets, except that here, the comet is an entire world. The tidal forces become so strong that the planet bulges and flexes on every orbit, its shape wobbling under the strain. Rocky worlds in decaying orbits face their own kind of undoing. Picture a planet roughly the size of Earth that has drifted too close to its star. First, its atmosphere would be stripped away, layer by layer, leaving the surface naked under fierce, unfiltered radiation. Any seas would boil off, and rocks would begin to soften into lava. As the planet moves closer still, the star's gravity could tear at its crust, setting off enormous quakes and volcanic eruptions. Eventually, the stresses could become so great that the world fractures. Pieces might break loose, forming a stream of glowing debris that spirals inward, each fragment joining the star in a final plunge. Seen from afar, the last moments of such a planet would be both terrible and strangely luminous. A gas giant might appear as a distorted shape with bright, streaming tails of gas. A rocky planet might flare as it crumbled, its fragments shining like embers tossed into a furnace. The star itself could briefly brighten, having swallowed the remains of the world that once circled it. When a planet is destroyed, its absence reshapes the entire system. The gravitational balance changes, and the remaining planets may slowly shift their paths. Debris from the destroyed world can rain inward, sprinkling nearby objects and even the star itself with heavy elements. Some compact stars called white dwarfs show clear signs of having swallowed rocky material, as if the dust of shattered planets still lingers in their light. In their strange spectra, astronomers read the ghost stories of worlds that no longer exist. Here in our solar system, the major planets are not currently on any such death spiral, and their orbits appear steady over the timescales humans can truly imagine. But stars do not stay the same forever. Our sun is gradually using up its fuel and losing mass in the process, which allows planetary orbits to drift outward very slowly. Far in the future, when the sun swells into a red giant, its outer layers are expected to reach out and engulf Mercury, Venus, and perhaps even Earth. Our world may not fall inward due to a spiraling orbit. Instead, the expanding star may simply grow large enough to swallow it. The result, though, would be just as final. Some of the dangers that threaten planets do not come from distant giants or collapsing orbits, but from sudden storms thrown off by their own stars. Our sun, from the safe distance of Earth, feels calm and familiar. In reality, it is a boiling sphere of plasma, threaded with magnetic fields that twist, knot, and snap. Among its most dramatic outbursts are events called coronal mass ejections, often shortened to CMES. In these eruptions, huge clouds of charged particles and tangled magnetic fields are hurled into space. These storms begin high in the sun's outer atmosphere, where magnetic field lines build up tension like tightly wound springs. When they finally reconnect, they release enormous energy, launching bubbles of solar material outward at tremendous speeds. Some lumber along gently and disperse into the void without much effect. Others race outward so quickly that they can cross the distance from sun to Earth in only a few days. When one of those fast storms is aimed directly at us, it can buffet Earth's magnetic field and trigger powerful geomagnetic disturbances. One of the most famous of these events took place in the 19th century. In the year 1859, an English astronomer named Richard Carrington was watching the sun when he saw an intense flash of light, a solar flare, unlike anything previously recorded. Not long after that brightening, Earth felt the impact of a tremendous geomagnetic storm. Auroras, normally confined to the polar regions, spilled far toward the equator, painting the skies with shimmering curtains of red and green over much of the world. In some places, the night became so bright that people woke thinking dawn had arrived, and miners in remote mountains reportedly began cooking breakfast under the ghostly glow. The telegraph, the cutting-edge communication technology of that era, reacted dramatically. Wires sparked, and some equipment caught fire. Operators received electric shocks from their instruments. In a few surprising cases, telegraph lines continued to send messages even after their power supplies were disconnected, driven purely by the electric currents induced by the storm in the long wires stretching across the landscape. It was as if the sky itself had stepped into the circuit. Our modern world is far more tightly woven with electricity than the world of Carrington's time. Power grids span continents. Satellites ring the planet, carrying signals for navigation, communication, and weather monitoring. Undersea cables and vast server farms help build the invisible web of the internet. All of these systems can be vulnerable to the kind of intense geomagnetic storm a strong coronal mass ejection can produce. A storm on the scale of the one in 1859 striking today could overload transformers, damage satellites, disrupt navigation systems, and knock out power over wide regions, at least for a time. Because of this, scientists keep a close watch on the Sunday spacecraft, such as the Solar and Heliospheric Observatory and the Parker Solar Probe, are dedicated to tracking solar activity and studying the origins of these storms. By monitoring the sun's surface and the space between us and it, they can give early warnings when a large eruption is seen, offering power companies and satellite operators precious hours or days to prepare, to adjust loads, to switch equipment into safer modes. Engineers reinforce parts of the electrical grid with devices designed to endure geomagnetic disturbances, hoping to blunt the worst of any blow. Still, there are limits to how much protection is possible. In the year 2012, a massive coronal mass ejection blasted away from the sun, similar in strength to the storm that caused the Carrington event. This time, Earth was not in its direct path. The storm swept through the region of space where our planet had been only days earlier. Many researchers believe that if that eruption had struck us head-on instead of missing, it could have plunged modern civilization into chaos. NASA scientists later worked through the numbers and quietly confirmed what many had feared, that near miss in the early 21st century could have caused damage counted in trillions of dollars, with some parts of the world taking years to fully recover. Power grids would be among the first to fall. A strong CME can drive powerful currents through long transmission lines, pushing heavy transformers far beyond their limits. Instead of a simple outage that can be fixed by flipping switches and rerouting power, a true geomagnetic superstorm could burn out equipment that takes months to build and replace. In the late 1980s, a much weaker storm was enough to knock out electricity across Quebec in less than 2 minutes, leaving more than 6 million people suddenly in the dark. That was only a small echo of what a Carrington-level storm might do. Above the atmosphere, the risk shifts from wires to fragile electronics. High-energy particles can scramble or destroy satellite systems, knocking out global positioning signals, weather monitoring, and communications. Airlines rely on satellites to guide their routes. If those signals vanished, flights around the world could be delayed or grounded. Financial networks depend on precise timing from satellite clocks. Without those steady beats, transactions can fail, markets can freeze, and digital systems can fall out of step. Even the seemingly untouchable web of undersea cables is not entirely safe. The glass fibers that carry beams of light beneath the oceans ignore magnetic storms, but the electrical stations that power and amplify those signals do not. If enough of those components were damaged, entire continents could find themselves suddenly cut off from the global internet, trying to coordinate disaster response with only local tools. And then there is the shadow of something larger still, a super flare. Stars across the galaxy have been seen unleashing eruptions thousands of times stronger than anything our sun has produced in modern history. These super flares pour out a flood of radiation and charged particles so intense that they can be noticed from light years away. If our own star ever released such a burst, Earth's magnetic shield and atmosphere would blunt some of the blow, but not all. Radiation levels could rise enough to endanger life at high altitudes, in space, and perhaps even at the surface in exposed regions. Food and water systems, hospitals, and communication networks would all be strained at once, and the recovery might be measured not in weeks, but in decades. The unsettling truth is that we cannot yet predict these events with comfortable certainty. We can watch the sun, track its cycles, and learn to read its moods, but flares and CMES still erupt with little warning. Once such a storm begins, there is no way to stop or divert it. The only question is whether our small world happens to be in the path when it arrives. Looking outward into the galaxy, astronomers see that fierce stellar tempers are common. Young, fast-spinning stars often carry tangled magnetic fields that store enormous energy. When those fields snap and reconnect, they release super flares so bright that telescopes pick them up across vast distances. Some of these outbursts unleash, in a few short hours, as much energy as our sun produces in an entire year. A red dwarf star called A.D. Leonis once provided a striking example. In the early years of the 21st century, observers watched it release a flare hundreds of times more powerful than anything recorded from our Sunday. If Earth had been orbiting that star at our usual comfortable distance, the blow would likely have torn away our atmosphere. Without that protective shell, the ground beneath open sky would have been bathed in intense ultraviolet and X-ray radiation, turning a living world into a scorched, silent one. Red dwarfs are small, but they are also numerous. Many of them host planets, including some that appear to sit in the gentle zone where liquid water could exist. Yet because these stars are dim, their habitable zones lie close in, where planets are exposed to frequent flares and, at times, super flares. Even if life emerged in such a place, it would grow beneath a sky that raged again and again, each storm a test of endurance. Super flares have also been seen on stars that look much like our own Sunday. Surveys of distant solar-type stars have revealed that some of them occasionally erupt with flares thousands of times stronger than anything we have yet measured here. Our sun has been relatively calm over the span of human observation, but there is no absolute rule that says it must always remain so gentle. Hints from Earth's own history suggest that it may have lashed out more fiercely in the distant past. Scientists studying tree rings and ice cores have found evidence of sudden spikes in radiation, recorded as unusual patterns in certain isotopes. One such burst, known as the Miyake event, appears to have occurred in the 8th century. Its exact cause is still debated, but it may point to an extreme solar outburst far stronger than anything ever seen by modern instruments. For planets circling other stars, these violent episodes can decide their fate. A world might form oceans, build an atmosphere, and cradle life, only to have repeated superflares gradually strip away its air or reshape its climate until it is no longer habitable. In some cases, The chemistry of the atmosphere may be altered so deeply that it triggers a runaway greenhouse effect or leaves the surface exposed to sterilizing radiation. Beyond storms and flares, there are slower, more secretive horrors, stars that steal from one another. Some stars do not simply burn through the fuel they were given at birth and fade. Instead, they live in pairs, and when one begins to swell and weaken, the other quietly reaches out and feeds. Astronomers call the strange, rejuvenated results blue stragglers, but it is easy to think of them as stellar vampires. In old star clusters, where most bright, massive stars should already have aged and dimmed, blue stragglers stand out as oddly youthful. They shine hot and blue in communities that should be dominated by cooler, redder suns. Their presence suggests cheating. Somehow, these stars have gained new fuel and a second youth. One way this can happen is through mass transfer in a close binary pair. When one star expands into a red giant, its outer layers become loosely held. Its smaller, denser companion can begin to pull that gas away, drawing it into a glowing disk before it falls onto the thief's surface. With this stream of fresh hydrogen, the companion brightens and heats up, looking younger than its age. The donor star, stripped and weakened, gradually shrinks back, sometimes becoming a white dwarf, a dense glowing ember of its former self. In crowded clusters, some blue stragglers may form through direct collisions or mergers. Stars move in complex, looping orbits, and now and then two of them can come close enough to merge into one. The new, more massive star burns hotter and brighter than either parent, even though both were already aged. For a time, it shines as if it were young, masking the long history written in its core. But even these stellar vampires cannot escape the deeper rules. Their borrowed youth is temporary. As they burn through their newly gained fuel, they, too, will swell, shed layers, and eventually end as white dwarfs, neutron stars, or black holes. In some of the most extreme cases, the feeding star is itself a white dwarf. As it gathers gas from a companion, the material piles up on its surface. When enough has accumulated, a runaway nuclear reaction can ignite, producing a Type 1, a supernova, a thermonuclear blast that tears the star apart and outshines its entire galaxy for a brief, dazzling moment. By tracing blue stragglers and related systems, astronomers can read the hidden history of clusters and binaries, seeing where stars once collided, where they fed, and where they died in borrowed light. Closer to our own world, another kind of cosmic threat has left deep marks: asteroid impacts. Earth's crust still carries the scars, though many have been softened by time, erosion, and plate tectonics. In the early days of the solar system, impacts were constant, part of the violent process of building planets. Over billions of years, the barrage slowed, but it never fully stopped. On human timescales, large impacts are rare. On planetary timescales, they are inevitable. The asteroid that ended the age of the dinosaurs was neither the first nor the last to strike Earth with devastating force. When a rocky body roughly a kilometer across crashes into a planet, it releases energy equivalent to millions of nuclear bombs. The immediate effects are brutal. A blinding flash, a shock wave that flattens everything for vast distances, and searing heat that ignites forests and grasslands. If such a rock falls into the ocean, towering tsunamis rise and race outward, sweeping across basins and pounding distant shores. Yet the longer aftermath may be even more dangerous. Dust, ash, and vapor thrown high into the atmosphere can dim sunlight for months or years, plunging the world into a kind of impact winter. Temperatures drop, plants struggle, and food chains falter. Around 66 million years ago, an asteroid perhaps 10 to 15 kilometers wide struck what is now the Yucatan Peninsula in Mexico, carving out the Chicxulub crater and setting off a chain of events that wiped out roughly 3/4 of all species on Earth. Other, older craters tell similar tales. In South Africa, the enormous Vredefort structure marks the site of an impact from an object that may have been more than 20 kilometers wide. In Canada, the Sudbury Basin records another ancient collision from an asteroid of comparable size. Each event reshaped the surface, altered climate, and quietly redirected the story of life. Unlike hurricanes or earthquakes, impacts do not follow seasons or fault lines. They arrive from deep space, their paths crossing Earth's orbit only now and then. To protect ourselves, we must first see them coming. That is why telescopes on the ground and in orbit spend so many quiet nights scanning the sky for near-Earth objects. NASA's Near-Earth Object Observations Program, together with international partners, tracks thousands of these wandering rocks, mapping their orbits and projecting their future paths. Most of the time, the rocks that share our solar system keep their distance. Most asteroids circle quietly in the main belt between Mars and Jupiter, held in place by a long, patient balance of gravity. They are like a distant crowd humming in the background, far from our daily lives. But that balance is not perfect. Tiny nudges from planets, especially from Jupiter, can slowly shift an asteroid's path, moving it from a safe lane into an orbit that crosses Earth's. Some of the most watched objects belong to families called the Apollo and Aten groups, asteroids whose paths bring them close to our planet again and again. Most slip past with nothing more than a line of numbers updated in a database. Yet even a small change in their trajectory, a gentle tug from another planet, a slight misreading of their orbit, could mean that one quiet passage becomes a dangerous one. A few asteroids have already made our hearts beat a little faster. One of them, called Apophis, is roughly 370 meters across. Early calculations once suggested it had a chance of hitting Earth in the years 2029 or 2036. Those first estimates were unsettling, but later, more precise measurements eased the fear, showing that it will pass safely by, at least for the near future. Another object, Bennu, is about 500 meters wide and has a small but non-zero chance of colliding with Earth late in the 22nd century. These are not planet killers on the scale of the dinosaur-ending impactor, but they are still large enough to flatten entire regions and disturb climate for years. If a dangerous asteroid were found to be on a collision course, the only truly comforting option would be to change its path before it arrives. The farther ahead we see it, the smaller the push we need. One of the simplest ideas is the kinetic impactor, sending a spacecraft to crash into the asteroid at high speed, giving it a tiny sideways shove. Even a small change, made years in advance, can add up to a miss instead of a hit. This is more than theory now. In the early 2020s, NASA's Double Asteroid Redirection Test, often shortened to DART, launched a spacecraft toward a small moonlet named Dimorphos, which orbits a larger asteroid called Didymos. The spacecraft struck Dimorphos on purpose, like a cosmic nudge. Afterward, astronomers measured the moonlet's orbit and found that its period had changed. It was proof, gentle but real, that a kinetic impactor can alter the course of a small world. Other ideas are more subtle. A gravity tractor mission would place a spacecraft near an asteroid and let its own tiny gravity tug on the rock over many years, slowly drawing the asteroid onto a slightly different path. More dramatic proposals involve using nuclear explosions, not to shatter the asteroid into a swarm of fragments, but to push it, either by detonating nearby or by heating one side, so that escaping material acts like a slow rocket exhaust. These methods carry risks. Breaking a large rock into many pieces might turn one catastrophe into a shower of smaller ones. Even with growing vigilance, we still have blind spots. Some asteroids approach from the direction of the sun, hidden in the glare until they are uncomfortably close. In the year 2013, a space rock about 20 meters wide entered Earth's atmosphere over Chelyabinsk, Russia. It exploded high in the air with an energy comparable to several tens of Hiroshima bombs. The shockwave shattered windows across the city and injured more than 1,500 people. No one had seen it coming. Its path had aligned with the daylight sky, where our current surveys are nearly blind. A few years later, in 2019, an asteroid close to 100 meters across slipped past Earth at a distance of about 70,000 kilometers, roughly 1/5 of the way to the moon. It was discovered only a day before its closest approach. Too small to end civilization, yes, but large enough to erase a city. Encounters like this are quiet warnings, reminding us that we need better eyes in space, especially telescopes that can watch from vantage points where the sun's glare does not hide incoming objects. For any specific year, the odds of a major impact are low, but the consequences of a single bad day are so profound that we cannot dismiss the risk. Unlike earthquakes or storms, asteroid impacts are, in principle, preventable. If we find the rock early enough, we can act. That is why space agencies and observatories around the world continue to refine their surveys, test deflection strategies, and quietly prepare for a moment that may never come, and yet, someday, might. The craters on the moon, on Mars, and across Earth's worn surface whisper the same message. Space is not empty, and some of the objects drifting through the dark do, from time to time, find their way to us. Far beyond the scale of planets and asteroids, whole galaxies are also shaped by collisions and hunger. They do not float alone. Instead, they live in a vast cosmic web, drawn toward one another over millions and billions of years. When a large galaxy meets a smaller one, their mutual gravity stretches and distorts them. Stars are pulled into long streams, gas clouds are torn apart, and, in time, the smaller system is absorbed. Astronomers call this slow consumption, galactic cannibalism. Our own Milky Way has played this role many times. One of its current meals is the Sagittarius Dwarf Galaxy, a small, elongated system whose stars are being peeled away and scattered. Great arcs of those stars now loop around the Milky Way, forming tidal streams that wrap the sky. This is not the first companion our galaxy has stripped, and it will not be the last. Over its lifetime, the Milky Way has likely absorbed many small galaxies, their identities blurred into our spiral arms and halo. In the centers of dense galaxy clusters, the process becomes even more extreme. There, enormous elliptical galaxies, known as brightest cluster galaxies, sit like cosmic monarchs. Over billions of years, they have devoured countless smaller neighbors, growing swollen and diffuse. One famous example called IC 1001, lies more than 1 billion light-years away and stretches roughly 6 million light-years from end to end. Vastly larger than the Milky Way, its size speaks of a long history of relentless mergers, each one adding new stars and gas to its bulk. Closer to home, our nearest large neighbor, the Andromeda Galaxy, is also busy eating smaller systems. Star streams and disrupted dwarf galaxies in its outskirts tell the same story of quiet consumption. Andromeda's most dramatic act, however, still lies ahead. It is moving toward the Milky Way at a speed of roughly 110 kilometers per second. In about 4.5 billion years, the two spirals will begin to interpenetrate and merge. From our perspective, that far future collision will unfold in slow motion. Vast as they are, galaxies are mostly empty space, so individual stars are unlikely to crash directly into one another. Instead, their orbits will be reshaped by shifting gravitational fields. Spiral arms will stretch into long, delicate tidal tails. Clouds of gas will collide and compress, igniting bursts of new star formation. Over time, the tangled structure will relax into a single larger galaxy, likely an enormous elliptical, sometimes nicknamed Milkomeda, the blended child of the Milky Way and Andromeda. At each galaxy's heart sits a supermassive black hole, millions or even billions of times the mass of the Sunday. During the merger, these central giants will slowly drift toward each other, shedding energy through interactions with stars and gas. Eventually, they will meet and merge, releasing a flood of gravitational waves that ripple through space like a last, deep sigh of the collision. Elsewhere in the universe, galactic encounters take on many shapes. The Antennae galaxies, for example, are a pair locked in a striking embrace. Their distorted arms stretch out like the curved feelers of an insect, pulled into sweeping arcs by tidal forces. In the regions where their gas clouds intersect, star formation has surged, creating bright knots of young stars. Another system, known as the Tadpole Galaxy, shows a long, trailing ribbon of stars, a smaller galaxy in the process of being pulled apart and absorbed, leaving behind a luminous tail that stretches hundreds of thousands of light-years. When gas-rich galaxies collide, their central black holes can be fed by the infalling material, turning otherwise quiet cores into blazing active galactic nuclei. In some cases, these powerhouses shine as quasars, their radiation outshining the combined light of all the stars around them. Slim, high-energy jets can lance outward across space, sculpting their surroundings on staggering scales. Even our Milky Way's graceful spiral shape carries hints of past mergers. Streams of old stars, subtle ripples in the disk, and the structure of the central bulge all suggest a history written by many smaller collisions. Looking ahead, the long-term fate of our local group of galaxies is fairly clear. The Milky Way, Andromeda, and their smaller companions will eventually coalesce into a single massive system. By then, our sun will likely be entering its own red giant stage, and whatever descendants of humanity remain, if any, would look up at a sky transformed. What seems fixed and calm to us is, on cosmic timescales, a slow, restless dance. Gravity's games grow even stranger when we turn from whole galaxies back to the motion of just a few bodies. When only two objects are involved, their paths are tidy and predictable. A planet orbits a star in a graceful ellipse, or two stars circle a shared center of mass in a stable pattern. The equations are well known, the motions repeat, but add a third significant mass, and the simplicity dissolves. The system becomes a three-body problem, still governed by gravity's laws, yet so sensitive to initial conditions that long-term predictions become exceedingly difficult. Three-body systems appear throughout the universe. Some begin as binary stars, disturbed by a passing third object, a planet, a stray star, or a compact body like a black hole. Others form in crowded star clusters, where gravitational encounters constantly shuffle stars into new arrangements. At first, they may orbit in a seemingly stable pattern. Over time, tiny asymmetries and interactions grow, and their motion becomes chaotic. For planets, the consequences can be severe. Imagine a world that orbits not one star, but a close pair. Even in the simplest case, its environment is complicated, as it must respond to the shifting pull of both suns. Now introduce a third massive object, a distant star, a giant planet, or a black hole passing nearby. The new gravitational tug can slowly distort the planet's orbit, making it more elongated, tilting its plane, or nudging its closest approach nearer to one of the stars. In some systems, these changes accumulate until the planet is flung outward altogether, ejected at high speed. The world becomes a rogue, leaving its home system behind and drifting through interstellar space with no star to circle. In others, the orbit decays instead of expanding. Subtle shifts push the planet closer to its star with each pass, until tidal forces and atmospheric drag hasten a spiral inward, ending with the planet's destruction in its star's fiery embrace. In dense clusters where many stars are packed into a relatively small volume, close three-body encounters are common. When three stars interact strongly, one is often kicked out of the group, while the remaining two settle into a tighter binary. Over time, this process helps shape the cluster's structure, deciding which stars remain bound and which are ejected into the wider galaxy. Some of the fastest stars we know, called hypervelocity stars, may be the exiles of such encounters, flung away at thousands of kilometers per second. Even the universe's darkest objects, black holes, are drawn into this kind of gravitational drama. They, too, can join unstable trios, feel competing pulls, and be hurled into new orbits by the shifting tides of the three-body dance. Near the crowded hearts of galaxies, where supermassive black holes lie hidden in swirls of stars and gas, gravity plays an even more ruthless game. Smaller black holes and neutron stars drift through this environment like stones in a storm. Close encounters with other massive bodies, or with the central black hole itself, can fling them outward at tremendous speeds, sometimes fast enough to escape the galaxy entirely and vanish into intergalactic space. Others are nudged onto paths that curve inward instead, bringing them closer and closer to the central monster until they are finally torn apart or swallowed. When two compact objects are driven together in this way, the final moments are anything but quiet. As black holes or neutron stars spiral in, they twist space and time around them, sending out gravitational waves, ripples that spread through the fabric of the universe. Detectors on Earth have already heard some of these distant collisions as faint, rising chirps, each one a record of a violent dance that began long ago in some crowded corner of a galaxy. The wildness of three-body interactions is part of why long-term planetary stability is never guaranteed with absolute certainty. A system of planets and moons may look calm and orderly for billions of years, but gravity remembers every disturbance. A passing star, a wandering rogue planet, or even the distant tug of another system can add just enough imbalance to start a slow cascade. orbits shift by tiny amounts. Those changes add up, and over immense spans of time, a once stable configuration can unravel. Planets may trade places, worlds may be thrown out, or they may be sent inward toward their stars. Some of the strangest exoplanet orbits we have found likely owe their shape to these tangled histories. A few planets travel on highly elongated paths, swooping close to their stars before swinging far back out into the dark, like stones on stretched slings. Others are locked into resonances, where their motion is tied to that of neighboring planets or stars in repeating patterns set by gravity's invisible metronome. To understand such systems, scientists use supercomputers to simulate millions of possible futures, watching how three or more bodies might move under their mutual pull. They cannot predict the exact path of any one object over billions of years, but they can see patterns. Which kinds of systems tend to eject planets, which tend to fall inward, and which manage to remain mostly intact. Gravity shapes the universe, but it does not always build tidy clockwork structures. Just as often, it creates chaos, scattering planets and stars, tearing things apart while it assembles others. That same restless pull reaches all the way to the dim edges of our own solar system, where another kind of hidden danger waits. Far beyond the familiar planets, beyond even the icy band of the Kuiper Belt, lies a vast and largely invisible realm called the Oort cloud. Instead of a flat disk, it is thought to be a huge, ghostly sphere of icy objects surrounding the sun, like a distant shell, perhaps stretching close to a light year from our star. Out there, the sun's gravity is very weak. Trillions of frozen bodies, leftovers from the early days of planet formation, drift in slow, cold orbits. For billions of years, many of them may have remained undisturbed, like snowflakes resting in deep shadow. But such calm is fragile. A gentle tug, a passing star, a wandering giant planet, or even the tide of the Milky Way's gravity can disturb these distant objects. A tiny change out there can send a comet's orbit tilting or stretching until it begins a long, slow fall inward. Some of these icy wanderers will swing harmlessly around the sun and return to the dark. Others may cross Earth's path as long-period comets, streaking through the inner solar system on orbits that can take millions of years to complete. Comets travel faster than most asteroids when they fall toward the sun, and their impacts can be even more energetic. A comet several kilometers wide striking Earth would release energy equivalent to billions of nuclear weapons. It could ignite global wildfires, raise massive tsunamis, and throw enough dust and vapor into the atmosphere to shroud the planet in darkness and cold. Some researchers suspect that at least a few of Earth's mass extinctions may have been triggered by such comet impacts, even if many others were caused by asteroids. Astronomers have identified times when other stars have passed near enough to the sun to rattle the Oort cloud. One such visitor, known as Schultz's star, slipped within less than a light year of our system around 70,000 years ago, while early humans were already walking the Earth. If it shook loose any comets, those icy bodies would still be traveling inward today, taking immense spans of time to reach the inner solar system. A future encounter may be even more dramatic. In about 1.3 million years, a star called Gliese 710 is expected to pass directly through the Oort cloud, coming to within roughly 0.06 light-years of the Sunday. At that distance, its pull could send vast numbers of comets tumbling inward. Most would never come close to Earth, but some fraction could be nudged onto paths that intersect our orbit. Even a handful of large survivors reaching the inner system intact would pose a serious threat to life here. Unlike near-Earth asteroids, which can sometimes be tracked for decades before a possible impact, long-period comets are masters of surprise. They spend nearly all of their time in the dark beyond our sight. Only when they fall inward and approach the sun do they warm up and grow bright, sprouting the glowing tails that make them visible to our telescopes. By then, the clock is already ticking. A large comet on a collision course might be discovered only months before impact, leaving very little time to prepare or to try deflecting it. We have already had a few unnerving reminders. In the 1990s, a comet named Hyakutake appeared suddenly in the night sky, having eluded detection until it was only a few months from its closest approach. It passed within roughly 15 million kilometers of Earth, about 40 times the distance to the Moon close in cosmic terms. In the second decade of the 21st century, another comet swept past Mars at a distance of roughly 140,000 kilometers, closer than half the gap between Earth and the Moon. Had such an object been aimed at us, our window to act would have been painfully short. Some astronomers imagine future observatories stationed far from Earth, perhaps beyond Neptune, watching the outer darkness for the first faint glimmers of incoming comets. For now, though, our best defense is a mix of growing survey efforts and simple good fortune. We can map many threats, but not all. There are even ideas that link the sun's long journey around the Milky Way to patterns in Earth's history. As our star orbits the galactic center, it may pass through regions where stars are more crowded or where gravitational tides are stronger, increasing the chance that the Oort cloud is disturbed. A few researchers have suggested that this might help explain possible cycles in mass extinctions, perhaps occurring every few tens of millions of years. The idea remains controversial, but it underscores how events far beyond our control can quietly influence life here. On still larger scales, some of the most frightening events in the universe occur when the most massive stars die. A typical supernova is already unimaginably powerful, briefly outshining an entire galaxy. But when truly enormous stars reach the end of their lives, they can produce something even more extreme, a hypernova. In these rare explosions, a collapsing star releases perhaps 10 times the energy of a usual supernova, often accompanied by narrow jets of radiation that slice through space as gamma-ray bursts. These hypernovae are thought to occur in stars at least several tens of times more massive than the Sunday. Such stars burn their fuel quickly, fusing lighter elements into heavier ones until their cores can no longer resist gravity. In a normal core collapse supernova, the result is often a neutron star or a black hole. In a hypernova, the collapse is even more violent. The core falls inward with extraordinary force, forming a black hole, while the outer layers are blasted away by intense shock waves. Gamma rays are the most energetic form of light. When a hypernova happens, twin beams of gamma radiation can shoot out from the poles of the collapsing star at nearly the speed of light. If one of those beams happens to cross a nearby planet, the effects can be devastating even across thousands of light years. The upper atmosphere would absorb the radiation, but in doing so could be badly damaged. Ozone might be stripped away, leaving the surface exposed to harsh ultraviolet light from the planet's own star. Over time, that exposure could threaten many forms of life. The hypernovae we have observed so far have occurred in distant galaxies, far beyond any danger to Earth. Still, they offer a glimpse of how violent such events can be. Astronomers estimate that for a gamma-ray burst to significantly affect life here, it would likely need to occur within a few thousand light years. That sounds comfortably far, but our Milky Way is wide and full of massive stars that could, someday, end their lives this way. Among the candidates that sometimes draw attention is a system known as WR104, a pair of stars located roughly 8,000 light-years away, including a type of massive strip star called a Wolf-Rayet. These stars are thought to be possible progenitors of hypernovae and gamma-ray bursts. Some observations suggest that the system's axis may be oriented in our general direction, raising the unsettling but still uncertain possibility that a future burst's beam could intersect our orbit. Another famous system, Eta Carinae, sits about 7,500 light-years away. In the 19th century, it produced a huge outburst known as the Great Eruption, briefly becoming one of the brightest stars in the sky. Today it is quieter, but its instability hints at a dramatic ending to come. Whether it will produce a hypernova and whether any jet would be aimed anywhere near us remains unknown. Even if no gamma-ray beam were pointed at Earth, a nearby hypernova would flood space with high-energy particles over long timescales. Those cosmic rays could slowly erode the atmosphere, increase radiation at the surface, and stress ecosystems. Some scientists have wondered whether past extinction events might have been influenced by such bursts of cosmic radiation from relatively nearby exploding stars. Yet these titanic explosions are not only destroyers, they are also creators. In the chaos of a hypernova, heavy elements are forged and flung into space. Gold and platinum, uranium, and many others, along with more familiar elements like calcium and iron. Over time, these materials mix into gas clouds that collapse to form new stars and planets. The iron in human blood, the gold in rings, the elements in the rocks beneath our feet, all of them bear the fingerprints of long-dead massive stars. There are even stranger possibilities on the frontier between what we have observed and what we only imagine. After a massive star collapses and explodes, the remnant that remains is often a neutron star, an object so dense that a teaspoon of its material would outweigh mountains. Some theorists wonder what might happen if the pressure inside such a collapsing star grew even stronger, squeezing matter beyond the neutron stage itself. In that extreme environment, they suspect a new kind of object might briefly exist, a quark star, formed where the pressure inside a collapsing star becomes so immense that even individual neutrons are forced to break apart. When matter is pushed to its absolute limits, even familiar particles begin to lose their identity. In an ordinary neutron star, the core is made of neutrons packed together so tightly that they resemble a solid sea of nuclear matter. A quark star, if such a thing truly exists, would go a step beyond. Instead of individual neutrons, shoulder to shoulder, its interior would be a deep, dense ocean of their building blocks, quarks, drifting free in a state unlike anything we can create on Earth for more than a fleeting instant. Neutron stars are born when a massive star runs out of fuel and collapses. Its outer layers are blown away in a supernova, while the core is crushed until protons and electrons fuse into neutrons. The result is an object so dense that a single teaspoon of its material would weigh billions of tons. But if the collapsing core is even more massive, the pressure may not stop at neutrons. It may squeeze them themselves apart, turning their structure inside out and creating a sea of quarks, up quarks, down quarks, and perhaps something stranger. Physicists sometimes call this exotic state strange quark matter, a mixture that, in theory, could include not only the familiar quark types found in normal matter, but also strange quarks. If that kind of matter is stable, then a quark star could persist without immediately collapsing into a black hole. It might be a little smaller and denser than a neutron star of similar mass, with a smoother surface, stronger magnetic fields, and slightly different ways of radiating heat and light. From far away, though, a quark star would look almost exactly like a neutron star, small, hot, and bright in X-rays and radio waves. Telling them apart would be like trying to distinguish two distant candles by the color of their flicker. Astronomers have suggested that quark stars might cool at different rates than neutron stars, shedding their heat more quickly or more slowly. A few compact stars that seem to cool faster than expected have been floated as possible candidates, though nothing is certain yet. Some of the ideas surrounding strange quark matter sound almost like science fiction. One particularly eerie possibility is that if strange quark matter is more stable than ordinary nuclear matter, it might be able to convert normal matter into its own state. In that picture, a tiny droplet of strange quark matter bumping into a neutron star could, in principle, spread through it like dye through water, transforming the entire star into a quark star. If two such objects collided, or if a quark star crashed into another compact body, the result could be a chain reaction of transformation and collapse on a stellar scale. Collisions involving these ultra-dense remnants would be among the most violent events in the cosmos. When two neutron stars merge, they already produce powerful gravitational waves and bursts of gamma rays. If one or both were quark stars, the outcome might be even stranger: an unstable object collapsing swiftly into a black hole, or a new, larger quark star blazing briefly with extraordinary energy before it settles. On Earth, particle accelerators, like the Large Hadron Collider, recreate a whisper of the early universe, smashing heavy ions together and briefly freeing quarks from their usual confines. These experiments help physicists study quark matter under extreme conditions, but they cannot yet answer the deepest questions about its long-term stability. If quark stars do exist, they would represent an entirely new chapter in the story of how stars live and die, perhaps even a brief stage on the way to becoming black holes. Finding one would not just add a new kind of star to our catalog, it would reshape our understanding of matter itself. For now, they sit on the edge of possibility, somewhere between the known and the imagined, like a rumor carried on starlight. Some compact stars, however, are not mysterious for what they might be, but for what they already are. Magnetars are neutron stars with magnetic fields so intense that ordinary language begins to fail. If a magnetar somehow drifted as close to us as the moon, its magnetic forces would be strong enough to erase data on every credit card and hard drive on Earth. Even at safe distances of many light years, they can unleash bursts of energy that ripple across space and brush against our planet. A magnetar starts life as a very massive star, far larger than the Sunday. When its fuel is exhausted, it collapses and explodes, leaving behind a neutron star. In a small fraction of cases, the newborn remnant spins rapidly and traps an enormous amount of magnetic energy. The result is a magnetic field trillions of times stronger than Earth's, and up to about a quadrillion times stronger than the field around a typical refrigerator magnet. At those levels, the magnetic field can distort atoms themselves, stretching them into long, thin shapes. Anything that ventured too close would be pulled apart at the atomic level, reduced to a haze of particles before it ever touched the surface. But magnetars are not only extreme in theory, they are restless in practice. Their monstrous magnetic fields twist and shear over time, building up stress in the solid crust that encases the dense interior. When that stress becomes too great, the crust cracks. These starquakes release sudden floods of energy, sending out intense flashes of X-rays and gamma rays. Some of the brightest high-energy bursts ever recorded in our galaxy have come from magnetars, brief flares that, for a moment, rival the output of many ordinary stars combined. In 2004, one magnetar about 50,000 light-years away produced a flare so powerful that it slightly disturbed Earth's upper atmosphere, altering the ionosphere and affecting radio communication, even though the star was on the far side of the Milky Way. Had it been much closer, the effects could have been far more severe. Some magnetars also produce puzzling bursts of radio waves, reminiscent of fast radio bursts, mysterious millisecond-long flashes that appear from various points in the sky. If magnetars are indeed responsible for at least some of these signals, it would suggest that their tempers are even more varied than we once thought, capable of everything from steady pulses to sudden, sharp cries. Despite their drama, magnetars are rare. Astronomers have identified only a few dozen in our galaxy, and their lifetimes as magnetars are relatively short. Over a few million years, a blink in cosmic time, their magnetic fields weaken, and they fade into more ordinary neutron stars. For a brief phase, though, they stand as one of nature's boldest experiments in pushing physical laws to their limits, twisting space, light, and matter in ways that are hard to fully imagine. Some of the universe's most unnerving possibilities, however, do not involve stars at all, but the fabric of reality they are made in. On the largest scales, the universe seems stable. Galaxies drift, stars are born and die, and the basic rules of physics appear to stay the same. We build our understanding on the idea that the vacuum of space, the empty background in which everything floats, is the lowest energy state possible, a quiet baseline. But there is a haunting alternative. What if the vacuum we know is not the true lowest state, but a false vacuum, a kind of temporary plateau in the energy landscape of reality? In that picture, there could exist a deeper, more stable state of the vacuum. The universe only appears calm because it has not yet slipped into that deeper valley. A common way to imagine this is to picture a ball resting in a shallow hollow on a rolling hillside. The ball looks stable where it sits, but somewhere nearby lies a deeper hollow. Given the right nudge, the ball could roll over the rim and settle into the lower valley. The move would release energy along the way. If the vacuum of space behaved like that, the consequences would be far beyond anything else we have discussed. In such a scenario, the transition from false vacuum to true vacuum would begin at a single point as a tiny bubble of the new state. That bubble would then expand at the speed of light, sweeping through space. Anything it touched would be transformed. Unlike a supernova or a gamma ray burst, which are violent but local, this would be everywhere the bubble reached, all at once. Inside, the laws of physics themselves could change. The strengths of the fundamental forces might shift. The way particles gain mass could alter. Atoms as we know them might not be able to exist at all. Planets, stars, molecules, chemistry, and life would be erased or reshaped into something unrecognizable. It would not just be the end of Earth or the Milky Way. It would be the quiet end of the universe as we understand it. Perhaps the most chilling part of this idea is that there would be no warning, because the bubble wall would move at the speed of light. No signal could outrun it. One moment, the universe would look exactly as it does now. The next, everything within reach of the expanding bubble would simply be different. There would be no time to see it coming, no way to prepare. How likely is this nightmare? The honest answer is that we do not know. But everything we have seen so far suggests that if the vacuum is metastable, only temporarily stable, the timescales involved are unimaginably long. Measurements related to the Higgs boson hint that our universe might sit near a boundary between true stability and metastability. Even if that is so, calculations suggest that vacuum decay, if possible, is likely to occur only after spans of time so huge that they dwarf the current age of the cosmos. The trigger could be a random quantum fluctuation, a tiny, spontaneous shift in energy at the smallest scales. It might also, in principle, be nudged by extremely high energy events, like collisions between the most energetic cosmic rays. People sometimes worry about experiments in particle accelerators, but the universe has been running its own far more powerful experiments for billions of years, smashing particles together at energies we can barely reach. If those natural events were going to trigger vacuum decay, they likely would have done so already. The fact that the universe has existed for roughly 13 and a bit billion years, surviving countless supernovae, black hole mergers, and other extremes, suggests one of two comforting possibilities. Either the vacuum is truly stable, or the odds of decay within any reasonable timescale are so small that, for all practical purposes, they might as well be zero. Unlike asteroid impacts or solar storms, which we can at least attempt to predict and perhaps one day mitigate, vacuum decay offers no shield, no warning, and no plan. It is more a thought experiment than an everyday worry, a reminder that even apparently solid foundations may hide deeper mysteries. For now, the universe holds together. Stars burn, planets turn, and the vacuum behaves as though it intends to go on doing so. And yet, even without such exotic endings, the ordinary ways that stars die are dramatic enough. Even the most steady, long-lived suns must eventually exhaust their fuel and begin, slowly and quietly, to loosen their grip on stability, entering the strange final acts of their lives, the slow decline toward death. For stars like our sun, the last chapters unfold slowly, over billions of years. As they age, they swell into red giants, their outer layers puffing outward and cooling, their gentle light turning deeper and redder. From a distance, it looks calm, almost graceful, but inside that swollen glow, something far less gentle is waiting. A sudden, hidden ignition called a helium flash. It is not the world-ending blast of a supernova, but an inward explosion in the star's core. A brief, intense moment that quietly rewrites its inner structure. This drama happens in stars with masses of roughly 0.8 to about 2.3 times the mass of the Sundays. Too small to die as supernovae, but large enough to live long, red giant lives. By the time they approach this moment, they have burned most of their central hydrogen. The outer layers expand into a vast, cool envelope, while the core, now mostly helium, contracts under gravity and becomes extraordinarily dense. In that compact heart, the rules change. The helium core enters a state called electron degeneracy. In normal stellar gas, as temperature rises, atoms move faster and push outward harder, and that pressure balances gravity. But in a degenerate core, pressure is set by quantum mechanics, not temperature. Electrons are packed so tightly that they resist being squeezed further, regardless of how hot the core becomes. So the core keeps heating up while its pressure barely changes. Helium ash continues to pile on. Gravity keeps compressing it, and the temperature creeps toward the point where helium nuclei can begin to fuse into heavier elements like carbon and oxygen. In an ordinary, non-degenerate core, fusion would start gently. The extra heat would cause the gas to expand, cooling the reaction and letting the star adjust. Here, there is no such safety valve. When the temperature reaches around 100 million degrees Kelvin, helium fusion ignites almost everywhere in the core at once, with pressure unable to respond. The reaction runs away. For a few moments, the core releases an immense burst of energy, comparable, in total, to the light of an entire galaxy, but bottled up deep inside the star. Surprisingly, we do not see this as a dramatic external blast. The star's enormous envelope acts like a blanket, absorbing and smoothing out the outburst. Instead of flying apart, the star rearranges itself. The helium core expands and cools slightly, breaking the degeneracy that made the runaway possible. The fusion settles down into a steadier burn. The red giant shrinks a little, brightens in a different way, and enters a calmer phase, quietly fusing helium in its heart. It is as if the star has undergone a silent internal detonation that does not destroy it, but nudges it into a new identity. In some stars, later evolutionary stages bring further pulses of this kind. On the asymptotic giant branch, a late phase, for sun-like and slightly heavier stars, helium can ignite in shells around the core in repeated flashes. Each outburst puffs the outer layers, drives strong stellar winds, and helps cast material into space. Over thousands and millions of years, the star sheds much of its mass, forming an expanding shell of glowing gas, a planetary nebula. The core, left behind, cools into a white dwarf, a small, dense ember of the star that once was. Helium flashes are not confined to the deep interiors of red giants. In some tight binary systems, a white dwarf, a compact remnant about the size of Earth, can steal helium-rich material from a companion star. As that helium piles up on the dwarf's surface, pressure and temperature rise. If enough accumulates, the helium can ignite in a brief, explosive flash, causing the system to brighten suddenly before fading again. These outbursts, sometimes called helium novae, are distant cousins of the hidden helium flash inside a red giant, but now acting on the surface of a stellar corpse. Under the right conditions, if a white dwarf amasses enough fuel, these processes can push it over a critical mass, triggering a full thermonuclear disruption, a Type 1, a supernova that tears the star apart entirely. Most helium flashes do not go that far. They flare, reshape, and then calm, but they are part of the same family of quiet thresholds, moments when a small internal change tips a star into a new regime. Our own sun is expected to experience a helium flash roughly 5 billion years from now, after it has swollen into a red giant. Because the sun sits near the lower end of the mass range, the event should be relatively modest compared with more massive stars. Still, it will mark a sharp turning point, the moment when our star's core truly leaves hydrogen behind and moves into the last sustained stage of its nuclear life. If the violent shifts inside aging stars feel unsettling, stranger possibilities wait deeper down in the behavior of matter itself. In the world of theoretical physics, there's an idea called strange matter, an exotic form of matter that might be more stable than the ordinary atomic material that makes up our bodies, our planet, and the familiar stars. All known matter is built from quarks, which come in 6 types: up, down, strange, charm, top, and bottom. Everyday protons and neutrons contain up and down quarks. Under the crushing pressures inside neutron stars, however, quarks might be squeezed into new arrangements. Some physicists suspect that in those environments, quarks could rearrange themselves into a state that includes strange quarks as well, forming strange matter. In some models, strange matter could be denser and, crucially, slightly more stable than normal nuclear matter. If that were true, then any ordinary nuclei touching a piece of strange matter might be encouraged to transform into the same state, rather like water freezing around an ice crystal. A tiny fragment of this substance is sometimes called a strangelet. In a nightmare scenario, a single strangelet drifting into Earth could slowly sink toward the core, converting the material it touches into more strange matter until the entire planet became a single, dense, dark lump. Whether this is anything more than a fascinating worry is very much an open question. Much depends on details we do not yet know. Is strange matter really more stable than the material in atomic nuclei? Would a strangelet carry electric charge that repels ordinary nuclei, preventing it from growing? Could small strangelets simply decay into normal matter before doing any harm? Some theories suggest that neutron stars might, under the right conditions, convert into strange stars made largely of strange matter. If so, collisions, starquakes, or other events could sometimes fling tiny fragments into space. On the other hand, if strange matter is not truly more stable, any such pieces might be short-lived curiosities, dissolving back into familiar particles long before they could trigger anything dramatic. Physicists have considered these risks carefully, especially when planning high-energy experiments on Earth. Nature, however, has been running far more extreme collisions for billions of years in the hearts of supernovae and the surfaces of neutron stars. The fact that the cosmos has not already turned into a uniform ball of strange matter is itself a reassuring clue. Even so, the concept nudges us to remember how much of our everyday reality depends on the particular way quarks choose to arrange themselves. There are other mysteries that arrive from above rather than within. Cosmic rays, high-energy particles, mostly protons and atomic nuclei, rain down on Earth constantly from space. Most of them are modest in energy and well understood, born in the shock waves of supernova remnants or the energetic regions around pulsars. When they strike the atmosphere, they collide with air molecules and create showers of secondary particles that spread across wide areas. But now and then, detectors catch something far more extreme: ultra-high energy cosmic rays carrying stupendous amounts of energy, millions of times greater than typical cosmic rays. They are rare. Each one is like a solitary bullet fired from some unknown cosmic accelerator. When one hits the atmosphere, it sets off a cascade so energetic that instruments on the ground, spread over many kilometers, can register its passage. Our usual explanations struggle with these events. The known mechanisms for accelerating particles, shock waves and supernova remnants, magnetic storms around neutron stars, turbulent flows in ordinary galaxies seem hard-pressed to boost particles to such dizzying energies to account for them. scientists look to more extreme environments, the jets of active galactic nuclei, where supermassive black holes fling matter outward at nearly the speed of light, violent regions in galaxy clusters, or processes tied to the very early universe. Some ideas even involve particles we have not yet seen directly. In a few models, ultra-high energy cosmic rays could be the decay products of super-heavy dark matter or relics from primordial physics beyond the reach of our laboratories. If true, each detection would be more than an astrophysical curiosity. It would be a letter from a deeper layer of reality, written in the language of energies we can barely imagine. Facilities such as the Pierre Auger Observatory in Argentina and the Telescope Array in Utah have been built to study these rare visitors. They combine large grids of particle detectors on the ground with instruments that watch the faint flashes of ultraviolet light produced when showers develop in the upper atmosphere. From these subtle signals, researchers reconstruct the energy and direction of the original incoming particle. Patterns are beginning to emerge. The highest energy cosmic rays do not seem to arrive equally from all directions. Instead, there are hints that they come slightly more often from certain regions of the sky, perhaps pointing toward nearby groups of galaxies or other large structures. Strong magnetic fields in and between galaxies likely twist their paths, so the tracks we see are blurred. Still, that faint anisotropy suggests that some part of the cosmic web may be acting as a natural accelerator. As ultra-high energy particles travel through space, they encounter the soft glow of the cosmic microwave background, the ancient light left over from the early universe. Collisions with these low-energy photons can sap energy from the cosmic rays over long distances. This idea leads to a theoretical limit called the GZK cutoff, which predicts that the most energetic cosmic rays cannot travel more than about 100 million light-years without losing much of their punch. Yet some detected particles seem to arrive with energies close to or beyond that expected limit, as if they have either started their journey relatively nearby or managed to avoid losing as much energy as our models suggest. That tension could mean our understanding of particle interactions at these extremes is incomplete, or that we are missing something subtle about how and where these particles are born. For us on the ground, there is little to fear from individual cosmic rays. Earth's atmosphere and magnetic field spread their energy out across wide areas, turning fierce single particles into gentle showers of subatomic fragments. Even the most extreme events are, from a human perspective, small. The real impact lies in what they can tell us. Each ultra-high energy cosmic ray is like a whisper from the deep universe, carrying information about environments and processes far beyond our reach. By listening carefully, by building bigger, more sensitive detectors, and by comparing their messages with what we know of galaxies, black holes, and fundamental particles, we inch closer to understanding how the cosmos shapes and reshapes its energy. And as immense as all these events are, helium flashes hidden in stellar hearts, hypothetical strange matter, magnetars cracking and screaming with gamma rays, cosmic rays punching through space at unimaginable speeds, they are still brief flickers against a much larger backdrop. Beyond the bursts and collisions lies a slower, quieter story, one that unfolds over incomprehensible stretches of time, the long cooling and fading of all things, the possibility that the universe itself may one day drift toward a cold and lifeless fate. Right now, the universe still feels alive, Stars burn brightly, galaxies collide, tangle, and slowly reshape one another. New suns are born from clouds of dust, old ones fade and fall silent. But this busy, glowing era will not last forever. The universe is expanding, and that expansion is gently stretching everything apart. With each passing moment, space grows larger, matter grows thinner, and the average temperature of the cosmos drifts downward, little by little. If this continues without end, it leads to a strangely quiet destination that physicists call the heat death of the universe. The name sounds fiery, but it is really about the opposite of fire. It is about a time when there is no more useful energy left, when everything is spread out so evenly that nothing interesting can happen. This fate is rooted in the second law of thermodynamics, the rule that says energy always tends to spread out. Whenever a star shines, it takes concentrated nuclear energy and turns it into light and heat, which race outward and then into the dark. Whenever a warm planet cools into space, it shares its heat with the cold around it. Bit by bit, the universe moves toward a state where energy is no longer clumped, but smeared out. For now, stars still provide contrast. The largest, hottest ones live fast and die young, burning through their fuel in only a few million years before exploding as supernovae. Smaller, cooler stars, like red dwarfs, can shine for trillions of years. Stars like our sun sit in the middle, living for billions of years before swelling into red giants and leaving behind white dwarfs, dense, cooling embers. On timescales far beyond anything our minds can easily hold, even these embers will fade. White dwarfs will radiate away their last warmth and eventually become black dwarfs, cold and dark. Neutron stars will cool. Planets, if they survive that long, will drift as frozen rocks around dead suns or wander alone in interstellar night. New stars will stop forming once the available gas has been used up or locked into remnants. There will be no new light, only leftovers. Even black holes, which feel so permanent, are not truly eternal. According to Stephen Hawking's work, they slowly lose mass by emitting a faint trickle of radiation, a process called Hawking radiation. For stellar mass black holes, this takes an astonishingly long time, far, far longer than the current age of the universe. But in principle, given enough time, they will shrink, dim, and finally disappear. What remains after all that is almost nothing, a thin, ghostly mist of low-energy particles drifting through an enormous, nearly empty cosmos. No galaxies, no stars, no complex structures. Motion itself becomes soft and slow. On this far horizon, the universe has not exploded or collapsed. It has simply run out of contrast, out of places where energy flows from hot to cold. With everything cooled and spread out, no work can be done. Heat death is not a dramatic bang, but a long, slow exhale, a cosmos that still exists, but no longer does. Some people imagine that even there, in that cold, quiet, tiny quantum fluctuations might occasionally spark something new, a brief, random ripple in the vacuum that could, in theory, seed new structures or perhaps even a new universe. These ideas are delicate and speculative, more like mathematical dreams than firm predictions. As far as we can tell, if the laws of thermodynamics hold the way we think they do, heat death would be a final state, not a sudden end, but an endless fading. Yet heat death is only one of the stories we can tell about the far future. All of them depend on a mysterious actor we still barely understand. Dark, energy. In the 20th century, astronomers discovered that the universe is expanding. At first, many expected gravity to slow that expansion over time, perhaps even reverse it. But in the late 1990s, observations of distant supernovae revealed something startling. The expansion is not slowing down, it is speeding up. To describe this, scientists use the term dark energy, a kind of energy woven into space itself that seems to push galaxies apart. For now, dark energy acts like a gentle pressure, stretching the universe at an accelerating but not yet catastrophic rate. In that picture, expansion goes on, galaxies drift away from one another, and heat death waits in the far distance. But there's a more unsettling possibility. What if dark energy is not constant? What if, over vast time, it grows stronger? In that scenario, often called the Big Rip, dark energy does not just separate galaxies, it eventually overpowers every kind of binding force. First, the gravity holding galaxy clusters together would fail. Galaxies in a cluster, once bound companions, would slip away from each other, accelerating into the dark. Later, even individual galaxies would no longer be safe. The Milky Way's gravity now keeps its stars bound in a graceful spiral, all of them orbiting a common center. In a Big Rip universe, there would come a time when dark energy's push becomes stronger than the Milky Way's pull. Stars would be drawn outward, leaving their galaxy and drifting alone. Still later, the same thing would happen on smaller scales. Planetary systems would be torn apart. Planets would be pulled from their stars. Moons would leave their planets. Eventually, dark energy would grow so strong that it would challenge the forces holding matter itself together. Stars would unravel into clouds. Atoms would be torn apart as electrons are ripped from nuclei. Finally, even protons and neutrons might be shredded, their internal quarks pulled apart by the ever-growing expansion. In the last instance of such a universe, there would be no galaxies, no stars, no atoms, only a rapidly stretching sea of elementary particles, and perhaps even those could not hold their form. Space-time itself might be so distorted that our familiar notions of distance and duration would no longer make sense. How soon could such a fate arrive, if it is real? That depends entirely on the true nature of dark energy. If it stays roughly as it is, the Big Rip will not happen, and the universe may simply drift toward heat death. If dark energy weakens, the expansion could slow or even reverse someday, leading to very different endings. If it strengthens over time, some calculations suggest that a Big Rip could arrive in a few tens of billions of years, a long time from our perspective, but much sooner than the far horizons of heat death. For now, observations do not yet tell us which of these stories, if any, is the one we live in. Dark energy remains a quiet mystery, felt in the motion of galaxies but still poorly understood. While we ponder the fate of the universe as a whole, there is another deep and tangled question hiding in smaller, denser corners of space. What really happens inside a black hole, and what becomes of the information that falls in? In classical general relativity, when a massive star collapses into a black hole, its core keeps shrinking until it forms a singularity, a point of infinite density where the theory itself breaks down. At the same time, everything that falls into the black hole, matter, radiation, the fine details of what it was, all seems to disappear behind the event horizon, the one-way boundary that even light cannot cross outward. Quantum mechanics, however, insists that information cannot simply be destroyed. This clash between the two pillars of modern physics is known as the black hole information paradox. Somehow, both sets of laws must be right, yet taken at face value, they disagree about what happens inside a black hole. Some physicists have proposed that the singularity never truly forms. Instead, they suggest that quantum gravity effects become important at extremely high densities and halt the collapse, creating a tiny, ultra-dense core called a Planck star. Its name comes from the Planck length, the smallest meaningful scale in our physics, far smaller than any atom. In this picture, the matter and information that fell into the black hole do not vanish into an abstract point. They are stored in this compact Planck star at the center, like a compressed archive. The event horizon still exists, and from the outside the object looks much like an ordinary black hole, slowly evaporating through Hawking radiation over an enormous span of time. As the black hole shrinks, the Planck star inside may eventually reach a point where it can no longer remain stable. Some models suggest that at this stage, instead of fading quietly to nothing, the Planck star could bounce, releasing its stored energy and information in a final, explosive outburst. To a distant observer, this might appear as a brief, intense flash of radiation, perhaps something akin to a gamma-ray burst, one of the bright, mysterious bursts we already observe scattered across the sky. In other speculative ideas, the interior of a black hole might pinch off and form a new region of space-time altogether, with the Planck star acting as a sort of boundary between our universe and a new one on the other side. In that case, black holes would not simply be dead ends, but strange seeds, planting new, expanding regions while appearing to us as dark, compact objects. These notions are intriguing, but they remain unproven. Planck stars, if they exist, hide deep within black holes, beyond any direct view. Their fingerprints would have to be read indirectly, perhaps in the detailed properties of black hole evaporation or in unusual bursts of radiation in the distant cosmos. As our telescopes become more sensitive, and as our theories of quantum gravity improve, we may begin to test some of these ideas more seriously. For now, Planck stars sit with quark stars and strange matter in that quiet borderland between mathematics and evidence. They offer possible answers to some of the deepest questions we can ask about information, about endings, about what lies beyond the horizons we can see, while reminding us that the universe is still full of secrets, even in the places we once thought were nothing but darkness. Neutron stars live on a razor's edge. Their gravity is so intense that if nothing pushes back, they would simply keep collapsing until they become black holes. For many of them, that is exactly what eventually happens. But some delay that fate in a strangely fragile way. They spin so fast that their rotation itself helps hold them up, the outward centrifugal force partly balancing the inward pull of gravity. Over time, though, the universe always collects its debts. These rapidly spinning neutron stars slowly lose energy, a tiny bit at a time. Their rotation slows, their stabilizing push weakens, and there comes a moment when it is no longer enough. There is no negotiation at that point. In less than a heartbeat, the star can no longer support its own weight. It collapses inward and becomes a black hole. This sudden, catastrophic change is sometimes called a blitzar. For as long as it spins quickly enough, the neutron star clings to existence. The instant its rotation drops below a critical speed, the entire structure gives way, The magnetic field that once wrapped around the star is chopped off as the event horizon forms. The field lines snap, and a tremendous surge of energy is released, not as a long, drawn-out explosion, but as a sharp, brief burst. Many astronomers think that at least some of the fast radio bursts we detect, millisecond flashes of radio waves that flare up from random points in the sky, could be the death cries of blitzars. These bursts are tiny in time but enormous in power, releasing as much energy in an instant as the sun might emit in days or weeks. Some burst only once, others repeat, suggesting a different origin. The puzzle is still open, with ideas ranging from highly magnetized neutron stars to more exotic possibilities. Blitzars sit among these candidates as a quiet, chilling explanation. A star that was there one moment and gone the next. Unlike a traditional supernova, a blitzar collapse leaves no expanding bubble of glowing debris to mark its passing. There is no slowly growing shell of gas, no long afterglow, invisible light. The neutron star simply vanishes behind a newly formed event horizon, leaving only its last burst of radiation to hint at what just happened. Such collapses could, in principle, happen anywhere, not just in distant galaxies, but within our own. If a blitzar were to collapse within a few hundred or a few thousand light years, and its high-energy radiation happened to be aimed directly at Earth, it could potentially disturb the atmosphere, damaging the ozone layer and letting more harmful radiation reach the surface. The good news is that the fast radio bursts we have seen so far mostly come from faraway galaxies, millions or billions of light years away. Known events are too distant to threaten us. Astronomers are nevertheless curious about whether any neutron stars in our Milky Way might be approaching that final tipping point. They study pulsars, spinning neutron stars that sweep beams of radio waves past Earth, like cosmic lighthouses timing their flashes with exquisite precision. As pulsars lose energy, their spins gradually slow. If one is heavy enough, there may come a moment when its slowing rotation can no longer support its mass. At that instant, it might become a blitzar. Neutron stars are common on galactic scales. There may be hundreds of millions in the Milky Way alone. Some of them could be hovering dangerously close to that critical balance right now, spinning down in silence. There are no warning flares, no long buildup. For most of their lives, they are simply steady pulsars. And then, in less than a second, they are gone. Future instruments, such as vast next-generation radio arrays, will likely detect many more fast radio bursts and track them more carefully, tracing their origins and patterns. As that catalog grows, we may learn which of those brief whispers come from magnetar flares, which from colliding objects, and which might be the final size of blitzars collapsing into the dark. If blitzars are examples of matter pushed beyond endurance, other ideas, imagine stars built from matter in far stranger forms. Not all theoretical monsters in the sky have event horizons. Some, at least on paper, could mimic black holes while remaining made of something else entirely. One such possibility is the boson star. While normal atoms are built from fermions, particles like electrons, protons, and neutrons that obey certain exclusion rules, boson stars would be made from bosons, particles that happily share the same quantum state. Under the right conditions, a huge cloud of bosons could condense into a single, coherent lump held together by gravity and by quantum mechanics working together. From far away, a very compact boson star might look almost exactly like a black hole. Its gravity would bend light and redirect passing matter in much the same way. Nearby stars might orbit it just as they would orbit a black hole of similar mass. Yet, unlike a true black hole, a boson star would have no event horizon, no point of no return. Its mass would be spread out in a dense, but still extended, cloud rather than concentrated in a singularity. Such an object would be almost invisible, emitting little light of its own. It might glow faintly from interactions in its outer regions, but nothing like the bright disks we sometimes see spiraling into black holes. Some scientists have wondered whether the supermassive objects at the centers of galaxies, which we currently believe to be black holes, might in a few cases be boson stars instead. If that were true, it would change how we think galaxies grow and evolve. Boson stars have also been suggested as a candidate for dark matter because they would interact only weakly with light. Large numbers of them could be lurking in galactic halos, shaping the motion of stars while remaining nearly invisible. In that picture, some of the missing mass we currently attribute to diffuse dark matter particles might instead be tied up in these exotic, compact clumps. Theoretically, boson stars could come in different sizes and densities. Some models describe extremely compact versions that are difficult to tell apart from black holes using only gravity. Others allow for much larger, more diffuse structures, like ghostly spheres of mass extending across many light years. In some cases, the mass distribution could be hollowed out, more like a shell or cloud than a solid ball. Detecting such objects, if they exist, would require careful listening to gravity itself. When a massive body passes in front of a more distant light source, its gravity can act as a lens, distorting and magnifying the background light. The precise pattern of this gravitational lensing depends on how the mass is distributed. A boson star might produce subtle differences in that pattern compared to a black hole. Gravitational waves offer another possible clue. When two black holes merge, they send out a characteristic waveform that observatories like LIGO and Virgo can detect. If two boson stars collided instead, or if a boson star merged with a black hole, the resulting waves might carry slightly different signatures, a faint hint that one of the objects was not what it seemed. In some speculative early universe scenarios, exotic boson fields might have clumped shortly after the Big Bang, forming primordial boson stars that have survived to this day. If so, they would be relics older than any normal star, fossils from a time when physics may have been very different. Another idea that tries to rewrite the story of collapsed stars is the gravistar. While boson stars change what matter is made of, gravistars change what happens to space itself inside a collapsing object. The gravistar concept was proposed as an alternative to the traditional black hole picture. Instead of allowing a true singularity to form, the idea imagines that quantum effects create a strange interior state that halts the collapse just before an event horizon fully develops. The result is an object that, from the outside, behaves almost exactly like a black hole, but whose core is something very different. In one version of this model, the interior of a gravistar is filled with a kind of quantum vacuum energy that exerts negative pressure, pushing outward. Surrounding this interior is a very thin, incredibly dense shell of normal or near normal matter. The outward push of the vacuum and the inward pull of gravity balance, creating a stable configuration without an actual singularity. To a distant observer, gravity around a gravistar would look nearly the same as around a black hole. Light would curve, orbits would form, and in falling matter would accelerate in similar ways, but there would be no true event horizon, no absolute boundary, beyond which nothing can return. Matter falling toward the surface might slam into the ultra-dense shell instead of disappearing forever. If gravastars exist, they would offer a different way to resolve the information paradox. Instead of information being lost in a singularity, it could be stored or transformed within the exotic interior region over long timescales. As the gravastar radiates energy, some of that information might, in principle, leak back out. Some speculative ideas go even further, imagining that the interior vacuum of a gravastar could be connected to the origins of new universes. In those pictures, the collapse that we see from the outside might correspond, on the inside, to the birth of an entirely new expanding region of space-time. Our own universe, in that story, could be the child of some ancient collapse elsewhere, its parent now appearing to us only as a dark, heavy object. At the moment, however, gravastars remain purely theoretical. Observations of black hole candidates through gravitational waves, high-energy light, and even the silhouette images captured by the Event Horizon Telescope are all consistent with the traditional black hole model. Many physicists believe that the paradoxes can be resolved within that familiar framework, without invoking new kinds of objects. Still, the possibility of gravastars and boson stars remains on the table, a reminder that our best current explanations might someday be replaced by something deeper. As our instruments sharpen and our theories evolve, we may learn whether these exotic alternatives are real inhabitants of the cosmos or just stepping stones in our imagination. And beyond even those lies another idea, more extreme still, that under the right conditions, even light itself could be packed so tightly that it collapses under its own energy, forming something very much like a black hole made purely of radiation, a Kugelblitz, a black hole born not from matter, but from light. Light usually feels gentle to us, a glow on a wall, a soft line across a floor. But in the language of physics, light is also energy, and energy has weight. Einstein's quiet little statement that energy equals mass times the speed of light squared means that in principle, enough light in a small enough space can bend space-time just as matter does. Follow that thought to its extreme, and you arrive at the Kugelblitz, a black hole made entirely of radiation. No collapsing star, no crushed core of iron, just an incredible flood of photons focused so tightly that their collective energy curves space into a trap. If enough radiation is squeezed into a small region, its energy density becomes so high that it forms an event horizon, and from then on it behaves like any other black hole. Once a Kugelblitz forms, it does not care how it was born. From the outside, it is simply a black hole, warping time, bending light, swallowing anything that crosses its horizon. The difference is in its origin story. Where a traditional black hole is the ash of a dead star, a Kugelblitz is what happens when pure energy collapses under its own gravity. Some dreamers imagine a civilization so advanced that it could deliberately create such tiny artificial black holes. A carefully formed Kugelblitz could, in theory, radiate energy through Hawking radiation, providing an extraordinarily efficient power source. Feed it mass, harvest the radiation, and you have a star in a bottle, dangerous beyond measure, but astonishingly potent. In the most speculative designs, a spacecraft might be driven by a small, engineered black hole, feeding it matter and using the emitted energy as thrust. It is the opposite of a chemical rocket's limits. Instead of carrying fuel that runs out quickly, you carry a tiny, enduring engine of curved space. It is an idea that lives firmly in the realm of theory, but it shows how deeply black holes are tied to ultimate notions of power. This same idea, turned darker, becomes a doomsday scenario. A Kugelblitz unleashed without control would not explode and fade. It would fall. If it plunged into a planet, it could, in principle, burrow inward, consuming matter as it went, growing heavier and more dangerous. Even a minuscule black hole has a fierce gravitational pull at close range. For now, though, the energies required to create one are far beyond anything we can touch. Even our most powerful lasers are like candles compared to the brightness needed. If Kugelblitzes do exist in nature, they are most likely relics of the very early universe, when radiation and matter were packed together at unimaginable densities. It is possible that some of the primordial black holes people speculate about began as regions where light itself collapsed. If we could understand such objects fully, we might learn more about the way gravity and quantum fields weave together. Not all cosmic violence is hidden behind horizons. Some of it erupts in open space, burning with such intensity that it briefly outshines entire galaxies and then leaves nothing behind. Most supernovae end with a remnant, a neutron star, or a black hole. Pair instability supernovae are different. They are the final act for the most massive stars, perhaps more than roughly 130 times the mass of the Sun, and they destroy themselves completely. In these giant stars, the core burns at temperatures of billions of degrees. At that heat, the core is flooded with high-energy gamma rays. Normally, these photons provide radiation pressure that pushes outward against gravity and helps hold the star up. But when their energy grows too high, they begin to transform into pairs of particles, electrons, and their antimatter partners, positrons. This process, called pair production, steals energy from the photons that were supporting the star. The outward pressure suddenly drops. Gravity seizes its chance. The core contracts rapidly, and in that brief collapse, conditions shift from unstable to catastrophic. Fusion rates surge. Instead of forming a compact remnant, the star's core undergoes runaway burning, and the entire star detonates. In a pair instability supernova, there is no neutron star left, no black hole, no dense remnant sitting in the center. The star is torn apart, all of its material hurled into space. The explosion can be hundreds of times more energetic than a typical supernova, bright enough to be seen from billions of light years away. For a time, it is as if a new beacon has been lit in the dark, announcing the final breath of a star that burned too hot for too long. These events are thought to be rare in the modern universe. They likely occurred more often when the first generations of stars were born, those early, nearly pure hydrogen and helium suns that may have grown to enormous masses. Their deaths would have seeded their surroundings with heavier elements: carbon, oxygen, silicon, iron, and beyond. Without such violent enrichment, later stars, planets, and life itself would have lacked the raw materials we now take for granted. Even today, astronomers occasionally find supernovae so luminous that pair instability is one of the few ways to explain them. A few famous events, discovered in the 21st century, may be examples. Explosions whose brightness and slow decay hint at massive stars tearing themselves apart entirely. If one were to occur relatively nearby in our own galaxy, it would be an astonishing sight, perhaps visible even in daylight, its light echoing through interstellar dust for centuries. At the right distance, it could also bathe surrounding space in high-energy radiation, reshaping nearby environments. Yet even these titanic events unfold on timescales of days and weeks. Some of the strangest explosions we have found last for much less time, rising and fading almost before we have fully turned our telescopes toward them. In recent years, astronomers have discovered a class of brief, blisteringly bright events known as fast blue optical transients. Their name is descriptive. They appear suddenly, glow strongly in blue light, and fade quickly, sometimes in only a few days. They do not behave like normal supernovae, which take weeks to climb and months to dim. The first of these to gain real attention was given a whimsically simple nickname, the Cow. Spotted in 2018, it flared in a galaxy about 200 million light-years away. It was astonishingly bright, dozens or even 100 times the luminosity of a typical supernova, but it faded far faster than the standard models could easily explain. It also poured out high-energy radiation, including X-rays, suggesting that something compact and powerful was active at its heart. Since then, other fast blue optical transients have been found, each with its own oddities. Some show strong radio emission, as if material is being flung outward at near light speeds. Others produce bursts of X-rays that rise and fall rapidly, hinting at an engine, perhaps a newborn black hole or magnetar, feeding and then quieting at the center. In many cases, astronomers see little or no evidence for a large, slowly expanding shell of debris, the hallmark of traditional supernovae. What, then, are we looking at? Several ideas compete. One is that some of these events could be failed or partial supernovae, in which a massive star's core collapses into a black hole, but a brief, intense release of energy escapes before the star is swallowed entirely. Another is that they might come from stars being torn apart by intermediate mass black holes, objects heavier than ordinary stellar black holes, but lighter than the giants at galactic centers. In such a tidal disruption, a star straying too close is shredded, and part of its material spirals inward, releasing a quick, powerful flare. Other hypotheses turn to compact remnants. Magnetars, with their extreme magnetic fields, can produce fierce bursts of radiation. If a magnetar were to suddenly collapse into a black hole, it might release a last, intense flash before disappearing behind an event horizon. Some fast blue optical transients share features that make this seem plausible, at least for a subset of them. There are even more adventurous ideas that these events could involve exotic forms of matter, strange internal transitions in dense stars, or new physics in how energy is converted and released. The trouble is that fast blue optical transients are, by nature, elusive. They brighten quickly and fade quickly. Catching them early enough to gather detailed data requires wide, sensitive surveys and a bit of luck. Their locations do not tell a simple story either. Some appear in galaxies rich with star formation and gas. Others occur in quieter regions where few massive stars are expected. The pattern, if there is one, is still hidden in small numbers and noisy data. So for now, these flashes remain another mystery in a sky already filled with them. Brief, blue, and strange, they arrive, blaze, and vanish, leaving behind only thin traces in our records, reminders that the universe is still capable of surprises, even after centuries of watching. After wandering through all these extremes, black holes of light, stars that unmake themselves entirely, explosions that flicker and fade almost before we can look up, it is easy to feel a little small, a little fragile. It might even nudge another question to the surface, softer, but no less unsettling. In a universe with so many ways to destroy, distort, or simply forget, what does it mean that we are here at all? Thinking about it, some philosophers and physicists have taken that unease and turned it inward, wondering whether our experience of all this might itself be an illusion, that perhaps, somewhere beyond these cosmic dramas, minds like ours are sitting in tanks or running on machines, watching a carefully crafted show. It is a thought experiment with a quiet, unnerving name: the brain in a vat. If thoughts can be fooled, as the brain in a vat idea suggests, then even our most terrifying visions might be nothing more than carefully crafted scenery. And yet, whether this universe is fundamental or simulated, the worlds it contains are harsh enough on their own. There are places out there where the worst dreams of fire and storm are simply weather. Some planets are so extreme that even Earth's fiercest deserts and volcanoes feel gentle by comparison. These are worlds where the air itself carries metals, where clouds are made of rock, and storms do not bring water, but knives and molten rain. One of the most famous is a gas giant called WASP-76b, roughly 640 light-years away. It circles its star so closely that it is tidally locked, with one side in endless day and the other in permanent night. On the day side, temperatures climb to about 2,400 degrees Celsius, hot enough to turn iron into vapor. In that blazing half of the sky, metals behave the way water does on Earth. They evaporate, rise, and drift as gas. Powerful winds sweep this metal-laden air toward the darker hemisphere, where temperatures are cooler still, around 1,500 degrees Celsius, but enough to let the vapor condense. There, droplets form and fall. Not water, not ice, but rain made of molten iron, glowing and deadly. If anyone could stand on some impossible platform under that sky, they would see shining drops of liquid metal drifting down through the darkness, hot enough to melt anything that met them. On Earth, we are used to a water cycle: oceans, clouds, gentle or heavy rain. On WASP-76b, it is the same physics written in a different language: iron instead of water, a furnace instead of a mild blue world. A spacecraft that tried to skim its atmosphere would need protection beyond anything we have ever built, shielding not only from fierce starlight but from metal droplets racing through the wind. Another planet, HD 18973b, sits about 64 light-years away and offers a different kind of nightmare. Its atmosphere is rich in silicates, tiny grains of glassy rock. Winds there may howl at speeds of roughly 8,700 kilometers per hour, several times faster than the speed of sound. Those winds pick up the silicate particles and hurl them sideways through the air. The result is a storm of glass, not gentle flakes drifting downward, but razor-sharp fragments driven sideways at supersonic speeds, like a planet-sized sandblaster made of shattered mirrors. Anything exposed to that storm would be worn away in moments. Metal surfaces would be scoured. Delicate instruments would be shredded. A human body would last only an instant. Some worlds go further still. Astronomers have found ultra-hot Jupiters whose temperatures rise above 3,000 degrees Celsius. In such atmospheres, elements we think of as solid titanium, aluminum, vanadium can appear as vapor. Clouds may form from iron or aluminum oxide or exotic titanium compounds, hanging heavy and dark above seas of churning gas. There are also ideas about so-called carbon planets, where carbon dominates more than oxygen or silicates. On such worlds, chemistry could favor graphite, carbides, even tiny diamonds. Their skies might be filled with sooty carbon clouds, their surfaces glazed with tar-like layers or sparkling with diamond dust. In some models, it could quite literally rain diamonds, small, crystalline drops forming deep in dense atmospheres before sinking toward the interior. Underneath the strangeness, the rules are familiar. The same principles that move water through Earth's skies can move iron, glass, or carbon through alien ones. Heat causes evaporation. Cooling causes condensation. Gravity draws droplets downward. Change the ingredients, change the temperature, and the same quiet equations paint very different pictures. These worlds invite a softer question as well. Could anything live there? Life on Earth has surprised us repeatedly, thriving around boiling hydrothermal vents, in acid pools, in ice, in radioactive ruins. We are learning not to underestimate biology's ability to adapt, but the planets of metal rain and glass storms push the limits of what we can imagine. If life existed in such places, it might not be built from water and carbon in the way ours is. It might use silicon or tungsten or other elements that laugh at heat. Its structures would need to survive temperatures that melt rock and winds that grind stone into powder. Its idea of comfort would be something we could not bear for even a heartbeat. For now, these possibilities are only whispers on spectra and curves in graphs. We know these planets mostly through the faint dimming they cause as they pass in front of their stars, and through the delicate fingerprints their atmospheres leave on starlight. We have never seen iron rain fall or glass storms blow with our own eyes. Someday, our instruments may grow sharp enough to map those skies in detail, to watch clouds form and vanish, to trace the pattern of storms around alien horizons. Perhaps distant probes, or their artificial descendants, will dip into those atmospheres and feel the heat and the hail of glass firsthand. Until then, we hold them in our minds as quiet, terrifying stories, worlds of metal rain, planets that scrape flesh from bone in a heartbeat, skies filled with soot and diamonds. They are reminders that the universe does not owe us gentleness. It can be beautiful and it can be brutal, often at the same time. And here we are, on one small, relatively mild world, listening to rumors of iron storms and glass winds, asking whether our reality is real, and letting these distant horrors lull us towards sleep. In the dark between stars and in the quiet behind your eyelids, the cosmos keeps its secrets. For tonight, it is enough simply to know they are there and that we are here, wondering about them.